Today, I'm going to present our recent work on understanding the so-called in-context learning phenomena um, by linear attention. And this is a joint work with my colleague Cengiz Pahlavan and our students Mary and postdoc Jacob and Annie Dintak. First of all, what is in-context learning? Many large networks have the ability to learn and execute tasks based on only examples seen in the input without any explicit pre-training. Now, let me give a concrete example. Suppose we have a sequence of input to a neural network. For example, we can do it on GPT, on ChatGPT, and I did it, and it worked out well. So this is the input that you can send to ChatGPT. It's a sequence of a pair of words, hello, follow, arrow, and a word, help, arrow, a word, so on and so forth. Now, and the last word, earth, arrow, but then you want GPT to guess what is the corresponding word you would need. Now, first of all, by going through the sequence, the neural network first have to understand that the task is to translate English words to the corresponding words in Klingon. And this is a task that they had to, the network had to realize. And also, once it is given this English word earth, also needs to do the correct translation to Terra. Now, this is so-called in-context learning because it's very unlikely that this task of translating English words to Klingon has been included in the training task. So, but somehow, with the pre-training on very large data set, neural network will be able to learn from this very short sequence what is the goal of this task and to perform this task. And this is sometimes referred to as in-context learning. And the goal of our project is to try to understand the underlying mechanism that enables in-context learning. So we're going to consider a mathematical formulation of in-context learning. So we suppose that we're given a sequence of input and output pairs. And here, xi, yi are the input and output. We have L of them, and then we call L the length of the context. And then for the last input, x of L plus 1, we are only given the input or the query token, and we want the network to produce, to predict the corresponding output y of L plus 1. Okay, and the statistical model that we assume is the following. We assume that the xi, yi, the input and output pairs are sampled from a joint probability distribution on a space of input and output, x cross y. So there's a joint probability distribution, but we do not consider only a single joint probability distribution. We assume there's a collection of joint probability distributions on x and y. So we use a calligraphic M to represent the collection of joint probability measures. Then for each such input sequence, we sample from a probability distribution of these collection of joint measures. That means we sample mu, that itself is a joint probability distribution on x and y from this probability distribution P on a set of n, okay? And then given this joint distribution, we are going to sample the sequence xi, yi independently from this joint distribution. So x1, y1, and x2, y2, and so on and so forth, they're all RID sampled from mu, but mu itself is sampled from this joint distribution, okay, P of n. All right, and then the pre-training, stage, the neural network essentially learns the prior distribution P of n. It learns a distribution on a space of joint probability measures. And then at testing time, in-context learning, the neural network is given a sequence of input and output pairs, x1, y1, up to xl and yl, and then essentially it performs a Bayesian updating step. Based on the input, it learns what is the conditional distribution on the space of probability measures. And then based on this conditional distribution, it generates the optimal y of L plus 1. Okay, this is the Bayesian setting that the most general Bayesian setting that we think will be able to model in-context learning. So I'd be very happy to take questions during my talk. We don't need to wait until the end. If there's anything that is not clear, I can address these questions now. All right.
Yeah, I
So,
have
yes.
a quick question about this model.
Yes.
So when you say a collection of joint probability distribution, so first, I guess the first question is that are we assuming the set is finite or?
So no, the set does not need to be finite, but conceptually it's easier. You can think about a finite set. So there will be, let's say, 10 different joint probability distributions on X and Y. All right. And then there's also a probability distribution on these 10 joint measures. Okay, so you can say they are equally likely. And then what we do is for each input sequence, we first sample one of such joint probability distributions. Okay, mu xy is one particular sample, and mu xy itself is a joint probability distribution on X and Y. Okay, and given this sample distribution, we are sampling the actual sequence xi and yi.
Yeah. So a related question is it useful to think of this as, I mean, the whole distribution as a mixture model, for example?
Yes, you can do that. Yes, exactly. It's essentially a mixture model. So given the, you first have a probability distribution on these individual joint measures, and then given the actual sample of the joint measure, and then we're going to sample the individual input and output pairs. Exactly, it's a mixture model.
Okay, thank you.
Yes, and then our hope that what the neural network is doing is a Bayesian updating step. Given the input and output pairs, it performs a Bayesian update of the probability measure on the space of the joint distributions. Okay, and then you are going to predict YL plus 1 from the optimal distribution conditioned on the previous input. All right. So this is a general setup. We're going to consider a much more simpler setting that is a special case of this general setup. This is the case for learning linear regression problems. Okay, so what is the actual setup? Again, we have a sequence of input and output pairs xi, yi. We're just going to assume that the output yi is given by the input through its projection onto a particular direction, which we call a task vector, omega, plus additional noise. Now, statistically, we assume that our input vectors are Gaussian samples from a Gaussian distribution. The noise is also independent over these sequences. Now, if you think about this model for each given task vector, then we have defined a joint distribution between the input x and output y. But then we additionally, we put a probability distribution on the task vectors. And this is what Ju was mentioning about the mixture model. So we have a probability distribution on W, but for each W, it specifies a joint distribution between x and y. Okay, and we're going to call these omega the task vectors. All right. And then what is a pre-training data set? The pre-training data set contains n different sequences of the input-output pairs. So here we use mu as an index for different training input sequences. And we use little n to represent the total number of input sequences in the pre-training stage. Okay, for each input sequence, it corresponds to one of the weight task vectors omega of mu. And then we're going to introduce this concept, so-called task diversity. We assume that at the very beginning of the training, we're going to sample k different task vectors, omega 1 to omega k, from the true probability distribution. And we're going to call this finite set of task vectors delta of k. And then once this delta k has been sampled, for each input sequence, we're going to sample a particular weight task vector from this finite set delta of k, okay, uniform at random. And in some sense, you can think about K as a measure of how diverse the task vectors are. K going to infinity will be the optimal case, but we're going to consider the case where K is large but finite. Okay. All right. Now, there are two Bayesian benchmarks. The first Bayesian benchmark is the following. Because this problem has been precisely specified, in particular, the task vector is assumed to be coming from this Gaussian distribution. If the neural network has perfect knowledge about this statistical model, then the optimal thing to do is to do the rich regression. And this rich regression would produce the Bayesian optimal estimator of the task vector. And correspondingly, if you can predict y by multiplying the input xl plus 1 with the optimal Bayesian optimal estimator of the task vector w. And omega. And omega is given by this formula. It's essentially just a rich regression estimator. Okay, that is one benchmark. That is we can consider this as the Oracle optimal estimator. Another benchmark is the following. Because in our setting, we assume that in the pre-training data set, we only have a finite number of different task vectors, omega 1 to omega k. Suppose the neural network has been specialized to these k different task vectors, then we can consider this discrete MMSE estimator that is still going to be a Bayesian optimal estimator, but the prior is not a true prior, which is joint a Gaussian distribution. The prior is just going to be a discrete distribution supported on these k different task vectors that we have provided in the pre-training data set. Okay. Correspondingly, this is the Bayesian optimal estimator using this discrete problem. Okay. So we have these two benchmarks. Okay. And the first one, the rich estimator, is supposed to be the optimal one, but the discrete MMSE is supposed to be the one that the neural network would implement if it is too much specialized to the pre-training task. So very interestingly, there's this paper by a group at Stanford University last year. They studied the same setup on a nonlinear transformer model, and they found the following interesting behavior. So here in this plot, the vertical axis shows the MSE, the lower the better. The MSE of the in-context learning performance, the lower the better. And the horizontal axis shows the number of different task vectors that we provide in the pre-training data set. Going from left to right, you are having more and more diverse task vectors in the pre-training data set. Now, the green curve is the performance of the discrete MMSE estimator, and the blue curve is the optimal ridge estimator. That is the Oracle optimal performance. The orange line is the performance achieved by a nonlinear transformer. I think the architecture is a GPT-2 architecture. Then you can see that empirically, the performance of a transformer-based architecture has a performance very similar to the DMMSE estimator when the number of pre-training tasks is not large enough. But when the number of pre-training tasks become larger, then the performance becomes closer to the rich estimator, which is the Bayesian optimal estimator that we should get. Okay, so there's some sort of phase transition. As you have more diverse pre-training data set, you are leaving the region of memorization. You're only memorizing the number of different task vectors that you've seen in a pre-training data set. You are actually be able to generalize to the unseen distribution. So part of the motivation of our work is to have a theoretical explanation of this empirically observed phenomenon. I can also take some questions if there's any question. So I don't have too many slides, so we can take questions along the way. All right. So here, this is our setting. We're going to consider this particular embedding scheme. So a transformer is essentially a mapping from a matrix to a matrix. So the matrix that we consider, the embedding matrix, is the following. Each column of this embedding matrix is a concatenation of one input and one output. Okay, starting from x1, y1 up to xl of yl. Okay, but then for the last column, we only have the input x of l plus 1, but we do not have the output, which is to be predicted. We put a 0 here. Okay. And then the particular architecture that we consider is a linear attention mechanism. So here, given the input z, we're going to apply this linear attention where K and Q are the key and query matrices, and V is the value matrix. And then there's also a skip connection, Z plus this linear attention produced a matrix. And then A is the final output. So I just want to comment that A has the same dimension as Z. So the input is this matrix and output is a matrix A of the same dimension. Eventually, we only care about a single scalar prediction, which is the output at the last column, Y. And then we're going to take the output matrix A, and we are going to take only its lower right corner, and that is going to be our output, predicted output Y hat of L plus 1. Okay, and this kind of embedding scheme has been previously used in the literature. So we're going to just follow this standard embedding scheme. Now, we're going to do some further simplification because in our problem, there are 3 trainable parameter matrices, the key, query, and the value matrices. Okay, and then eventually we only care about a single scalar prediction, y hat. First of all, we're going to write the value and the key and query matrix in a block form. And after some simplification, which I don't want to go to the details, we can convert this problem into a linear setup. So here we have combined the key and query matrix into a single trainable parameter n. So eventually, we can show that the output y hat can be written as an inner product between a matrix gamma, which contains the trainable parameters, and another matrix H of Z, which consists of only the training input. Okay, so here H of Z is a matrix formed by the input sequence matrix. And then gamma is a matrix of trainable parameters. And the final prediction is just a linear inner product between gamma and H, which we call the feature matrix. Okay, so this is the setup. And then the training problem target is a least square fitting. So here we have the true labels or true output Y, and inner product gamma of H is our predicted output, and with additional rich regularization terms. And here gamma is a matrix contains all the parameters that we can tune. And the features H of Z is a matrix form, is a D by D plus 1 dimensional matrix. And this feature matrix has this form. Essentially, it's a rank 1 matrix of an outer product of the last input vector and a row vector formed in this way. Essentially, a row vector formed by different output labels at different locations of the input sequence. Okay. Now, because this is a quadratic problem, so we have a very simple closed form solution. So we know that after training, the optimal parameter, which we call gamma star, itself is a matrix, but we can vectorize it into a vector, can be written in this form. And here, this matrix inverse is just one of the so-called resolvent matrix. Okay. So it's
yeah,
yes.
question about slide 10,
Slide number 10. Yes.
When you pass to the linear system. So that's a little bit surprising. So do you have any intuition why that can be written as a linear system? Because
yeah. So this is
on the left, obviously it's cubic, right? It's
right.
cubic,
That's right.
right? So
you're right. So thanks for these questions. Yeah. So here, first of all, we written in this way is a cubic system because you have V, K, and Q. The first simplification that we have done is to combine K transpose and Q into a single matrix. So this problem becomes quadratic, right? K transpose Q is combined into a single trainable parameter matrix M. So its problem is becoming quadratic. The second, but still it's non-convex. It's not a linear system. The second simplification is that we are going to set certain entries of V and N to 0, and there are some justifications for why this is a good approximation to the actual problem. If you've done that, then you can see that the problem becomes a linear system. So here you can see that gamma, this is the trainable parameter. It still depends on V and M in a quadratic way, but we have combined M and V into a single matrix gamma. So here y hat, this y hat is not exactly the same as the y hat here. It's an approximation.
I see. I see.
Yeah, but there are some argument for why this is a good approximation. Empirically, it's a pretty good approximation.
I see. I see. Okay.
And this approximation is just to make the problem tractable.
Mm-hmm. Okay.
All right, great. So and then so this is in terms, once we have done this linear approximation, then this problem is a quadratic. It's a least square problem. So then we have a closed form solutions for the optimal weight vector. So the actual work is to analyze this quadratic optimization problem in the high dimensional limit. Here. All right. So a few performance metrics. The first one is the so-called generalization error. And here Y and H is a pair of new input and output input given by HZ, and Y is the output label, that they are not part of the pre-training data set, and gamma star is the optimal weight parameter matrix that we've learned. And then we evaluate it using some test distribution. Then we are going to consider two different settings. The first setting is so-called in-context learning setting, where the test distribution is a true distribution, but it's different from the distribution of the training data set. Because in a training data set, we only have a finite number of different task vectors. So the training distribution is different from the test distribution. And we consider test distribution to be the true distribution. Now, the second case, we call it the in-distribution generalization, IDG setup, where the testing distribution is the same as the training distribution. And in the training distribution, we first have a finite k number of task vectors, omega 1 to omega k, and then the training distribution is a uniform distribution on these k different task vectors. Okay, so there are two different settings. Okay, they differ in terms of the probability distribution p over which we evaluate this expectation. Okay, and ICL is the performance we care about, and IDG is the performance is a benchmark that we want to see is the optimally learned weight matrix or the neural network too much specialized to the task vectors provided in a pre-training data set? Is that memorizing versus is it generalizing? And then we're going to consider the so-called joint asymptotic limits. So in a high-dimensional setting, and here we have a few parameters. D is the so-called token dimension. We have an input x I, and then we assume all these input vectors are d-dimensional vectors. Then D is considered to be large. And then we also have this number L, context length. How many different input and output pairs that we need to provide to the neural network? We use L to represent the length of the input sequence. And then N is the total number of such sequences that we provide in the pre-training data set. Okay, that is N captures a sample complexity. And finally, we have this number K, a so-called task diversity, Because in a pre-training data set, we only have a finite number of different task vectors, and k is the number of these task vectors. The larger the value of k, the more diverse the pre-training data set is. So we have these 4 different numbers, and we're going to consider this scaling regime that L, the context length, scales proportional to the dimension D, and K, the task diversity, scales proportional to the dimension D. And finally, the number of training samples N scales quadratically with dimension D. So it's N over D squared is considered to be an order 1 constant. So we are going to consider the large D limit. So although our result is consider a finite large D limit, but actual result is a finite sample. So we just need to consider the case where D is large. For example, in the range of D equal to 100 or 200, and then want to see what happens to this problem when D is relatively large. And again, we have these 3 important metrics. One is the sample complexity. How many samples do we need in a pre-training data set? And context length. How many examples do we need to provide in each input? And third one is the task sample complexity. How diverse should these tasks be in a pre-training data set? All right. So the main technical result of our work is the following asymptotic prediction. We say that the generalization error of this learning problem in the ICL and IDG setting both have well-defined limits as the dimension grows to infinity. And here, these quantities that depend on the parameter tau, alpha, and lambda determines the limits. And here, let me just give you the formula. So you don't need to focus on the specific details of this formula. The point of me showing this formula is just to say that all these generalization errors have well-defined deterministic limits that are only determined by these global parameters, these finite number of global parameters in a problem setting. Now, and the actual form of these global deterministic limits are too complicated. Let me just show you some numerical results. And here, the figure on the left shows the generalization error for the ICL task as a function of the sample complexity. So here, the horizontal axis is the number of training samples divided by dimension squared. From left to right, we are having more and more training samples. And the lines, the green and orange or red lines are the theoretical prediction from our theoretical results. And they differ in terms of the value of lambda, which is a rich parameter. So lambda equals 0 means we're doing a ridgeless regression problem. And you can see that there is a double descent phenomena at tau equal to 1. So when n is exactly equal to d squared, the generalization error goes to infinity. And otherwise, there is a double descent phenomenon. And here the symbols, the dots, are the simulation results if we train a linear transformer, and this is what we get. Okay, the purpose of this figure is to show, first of all, the theoretical prediction is an accurate captures the actual performance of this learning problem, and second, there is also a double descent phenomenon, and similarly, we also have in this case a different curve, but then the difference is that instead of changing the value of lambda, we set lambda, the rich parameter, to 0, but we change different values alpha. And alpha is the so-called context length. Alpha increases means you are having longer and longer sequences. I thought there was a question. Okay. But again, the theoretical curve, so some of the formulas are provided here, can predict the numerical value of the generation error. Some further experiments, and then you can see that this generation error is also not monotonic. There's this interesting phenomena. So when we change the length of the context length, previously we thought that it should be a monotonic behavior because the longer the context length, the better, the easier the problem is, and then the better the generation or the lower the generation error should be. But interestingly, for certain parameter settings, there's a non-monotonic behavior. So there's an optimal context length beyond which the generation error actually slightly increase. So going back to this original motivation of our work, there are two Bayesian benchmarks. The first benchmark is that if the neural network is aware of the entire probability distribution, in particular, it knows what is the distribution from which the task vector is sampled from, then optimal strategy is to perform this rich estimation and with a correct rich parameter set to be equal to rho. And this is the optimal Bayesian optimal performance. The second benchmark is so-called discrete MMSE. This is the case when we are performing, again, a Bayesian optimal estimation of the task vector, but a prior, instead of choosing the true prior, we are using the prior focused on only the finite number of task vectors that are provided in the pre-training data set. Okay, so this is the discrete Bayesian optimal estimator. Okay, these are the two benchmarks. And as I mentioned earlier in this paper, empirically, it has been observed that as you increase the diversity of your task vectors in the pre-training data set, the performance of a transformer-based architecture can go from memorizing, meaning that it achieves the same performance as the discrete MMSE estimator, to generalization. That means it approaches the optimal rich estimator using the true prior. Okay, because in the pre-training data set, you never see the true prior. You only see a finite sample of the true prior. Okay, there is this transition from memorization to generalization. So in our theory, of course, I want to emphasize that this empirical result is done on a multi-layer transformer architecture with nonlinearity. So in our work, we only considered a one-layer linear transformer architecture with some further simplification. But still, we can see a very similar transition. And here in this slide, it's a little bit busy, so let me just go through it slowly. The horizontal axis is the diversity of your pre-training data set. So K is the number of different task vectors in a pre-training data set. As you move from left to right, you are having more and more diverse pre-training data set. And the vertical axis shows the difference between ICL task and IDG task. So it can be treated as a surrogate measure of how much generalization we are having. Because if there's still a very large gap between ICL and IDG, that means you are not really generalizing to the true prior. You're only memorizing all these finite number task vectors. If this difference is converging to zero, that means you're getting you're generalizing to the true prime. And here, the curves, blue and orange and the red curves, show this difference as we increase the diversity. You can see that initially, when the diversity parameter kappa is less than 1, these two curves have a very slow slope. But once kappa is greater than 1, then the slope becomes much sharper, and asymptotically, this gap grows to 0 at the rate of 1 over kappa. Okay. Now, in contrast, the gray symbols represent what we will get if the network is only memorizing the finite number of task vectors. If that is the case, then this curve would grow to 0 much, much slower at a rate of 1 over kappa to the power of 2 over d. So this is a very, very slow rate. But you can see that when kappa is small enough, then our linear transformer is doing something similar to the green line. But once kappa goes above the threshold, then it deviates from this green line and achieves generalization at a much faster rate. Okay, so this is in some sense captures what happens in this empirical observation. Although the actual transition is at a different value, I think the difference is because we are studying a simple linear transformer architecture, but in this paper they studied a much more powerful architecture. All right. So we have also done some experiments on multi-layer nonlinear transformers just to verify some of the key observations that we obtained or insights that we obtained from the theory is still valid, at least qualitatively. So first experiment that we have done is the following. We considered the generalization error as a function of a sample complexity. You can see that indeed the scalings that we consider seems to be correct. There's still a double descent phenomena, and there is also a interpolation threshold at this point, and this n over d squared seem to be the correct scaling. And here n is the number of training samples, and d the dimension. So n should be proportional to d squared. And this is the scaling that we have used in the linear regime, but it also seems to be the right scaling for a nonlinear architecture. And for the figure on the right, we consider this so-called interpolation threshold just to further verify that whether n should scale as a d squared. And this seemed to be reasonable because here the gray line is a theoretical scaling line if we have a perfect quadratic scaling. And other lines are the empirical scaling curve for the interpolation threshold for different nonlinear architectures. You can see, roughly speaking, they follow this quadratic scaling regime. All right. So this is what I want to say about this this problem itself. But I want for the rest of my talk, I want to spend a little bit of time to talk about the underlying mathematics of our analysis. But this is also a good time to pause in case there's any question about what I presented so far.
So the previous slides about double descent. So this one, yes. So this is not the typical kind of double descent curve that people plot, right? This is with respect to the, I mean, the horizontal axis is actually the effective sample size, right?
You can think about this as the effective number of training samples in a pre-training stage, and
Right.
effective in the sense that we are scaling it by d squared. Yeah. So
Right.
still moving from left to right, you are having more and more samples in the pre-training data set.
But is the model fixed here? I mean, it's sorry, it's not. I shouldn't say model fixed. Is the architecture fixed at least?
The architecture is fixed. The difference is only how many tree training samples we provide to the same architecture.
Right. Because
But yeah, but there's no, I mean, at least this in the linear setting, we do not have a theoretical explanation, but at least for the linear setting, it's pretty clear what happens because at the end of the day, we are studying a linear regression problem, so there is always a matrix inverse. And at this interpolation threshold, the matrix to be inverted is singular. That's the reason why we have a big explosion of everything.
yeah, I think the question here is that when we say the interpolation regime versus what's the other regime we call it, memorization or?
So the so-called interpolation regime is below 1 when you do not have enough training samples. The capacity of the model is such that it can perfectly predict
Right.
all the labels. So the training error is 0. So if we plot the training error between 0 and 1, the training error is 0. But above 1, the training error becomes non-zero because you cannot fit everything.
Right. Yeah, I mean, I'm not familiar with this kind of double descent curves. But you know, the other kind of double descent curve that people plot, like you know, the typical work by, let's say, by Boken, right? So I think they are the second descent normally is for the case where your samples are sparse, right? When your model capacity is significantly larger than your training set, right? So, and typically there, I think the error is smaller for the second stage. That means when your model capacity is sufficiently large compared to the sample size, right? But here it seems like it's the opposite trend because the vertical axis is the prediction error.
Yes. Okay, it's a good point. Yeah. So yeah, we are not saying that we have the same model, but we have more and more data. Yes. So we're not saying that we are growing the model size. Yeah.
So this one is saying that actually fix the model, and if I grow the training set, then actually I enter a stage where the prediction error is actually lower. So
Yes, that's right.
yeah, that's a little bit. I mean, I know that
but I wouldn't be surprised in the specific setting of linear regression, the underlying mathematical reason is the same.
Okay.
Because
But
here, the integration threshold is just the matrix. The matrix is singular, and for the standard double descent phenomena, it's the same mathematical reason why you have a peak.
right, but it seems to me that the trend is opposite, right? Because the other kind of double descent is normally the second descent stage, they get a lower test error, and that stage is where your model is much powerful than your training set, right? But this one is opposite, right? This one is when your training set is much larger than your model capacity, then you get lower error, right? So it seems to me the trend are opposite, right, to what people typically observe
It's a good point. Yes, it's a good point.
Okay.
All right. Okay. All right. So I want if there's no other question, I want to switch gears a little bit and talk a little bit about the underlying mathematics of this analysis. So because the simplifications that we have done, this is a very simple problem. This is quadratic. It's a rich regression problem. So the optimal parameter matrix has a closed form solution. The only technical challenge or technical work to do is to analyze it. So then this is analyzing this resolvent matrix. And the only thing that is different from the standard analysis of high-dimensional rich regression is that all these feature vectors is a vectorized version of a matrix that has this tensorize form. So there is a more challenging correlation structures that is going on. So interestingly, this kind of a problem has been studied in some recent line of work about studying so-called nonlinear random matrices. So let me just briefly describe what is the key insight from this recent line of work from studying nonlinear random matrices, and then I'll come back to the connection to our problem. So first of all, let me recall a few classical random matrix models that people have studied over many decades. So here, let's assume that we have a data matrix X of dimension D by N, and each column of X is a independent data vector. Now, if we consider this matrix X times X transpose, this is just the empirical covariance matrix, then it is known that when the dimension of these data vectors, D, and number of these vectors, N, both become large in a proportional way, then the empirical eigenvalue density of this matrix X times X transpose will have well-defined limits. And here, the blue histograms are the empirical histogram of the eigenvalues, and the red lines are the theoretical limit curves, and these are so-called Marchenko-Parser distributions. And they're also a non-symmetric version. So instead of considering the same matrix and product multiplied with its transpose, we can consider the product two random matrix F and X. But in the past several years, there's been a lot of interest in studying nonlinear versions of these matrix ensembles. Here, if you look at X times X transpose, again, this empirical covariance matrix, we're going to apply a nonlinear transformation sigma to this matrix. And here, sigma is a one-dimensional function. So you're going to apply this nonlinear function, for example, a Yue Lu function, to each entry of X times X transpose. So it's an entry-wise nonlinear transformation of this matrix. And this kind of a nonlinear version appears in different settings. For example, when you study kernel method, and the sigma can be the kernel function. It also appears in so-called random feature models, nonlinear matrix factorization, or in robust statistics, you want to study the shrinkage of the empirical covariance matrix. And in the attention blocks, there's also this kind of linearity appearing, right? But this kind of matrix have been studied very actively in the past several years, and there's just very interesting equivalence principles that people have discovered through the study of these matrices. Broadly speaking, this equivalence principle is saying that the nonlinear model, in many cases, is equivalent to a linear model plus noise. Just to be concrete, consider this nonlinear random matrix, where you apply a entry-wise nonlinear transformation to this empirical covariance matrix. And let's call this nonlinear random matrix A. So in many cases, A is equivalent to a model B, which is a linear combination of three matrices. The first matrix is an O1 matrix, weighted by a constant mu0. The second matrix is the empirical covariance matrix X times X transpose, weighted by another scalar mu1. The third matrix is an independent noise matrix Z. Z here is just an independent symmetric Gaussian matrix with additional scalar parameter mu2. Okay, so in other words, this equivalence is saying that this nonlinear matrix is equivalent to a linearized version of this matrix plus additional independent noise. Okay, and this is so-called equivalence principle. It appeared first in this paper by Chen and Singer in the random matrix theory literature, and more recently it has also been studied in the context of random feature models and high-dimensional regression. Right, and over the past couple of years, I've also been studying this kind of matrix with a number of collaborators in different settings. Let me just provide you a very high-level picture of what's going on. How do I now understand this this equivalence principle? What is the underlying mechanism behind this equivalence principle? So here, to me, the best way to understand this equivalence principle is to first rewrite this nonlinear transformation in terms of a linear combination for polynomials, in particular the Hermite polynomials. So Hermite polynomials is a family of orthogonal polynomials, and here I give the first four such Hermite polynomials. Okay, and the properties that we know about Hermite polynomials is the following: they form an orthonormal family of polynomials with respect to the Gaussian measure. Okay, and in particular, this is a complete orthonormal family, so that means any square integrable function sigma, for example, Yue Lu, can be written as an infinite linear combination of these Hermite polynomials. And mu0, mu1, so forth are the combination coefficients. These are the scalar coefficients. Okay. Now, if you want to study this kernel problem where you apply a nonlinear transformation to the entries of this inner product matrix or the sample covariance matrix, because sigma can be written as a linear combination of these Hermite polynomials, correspondingly, you can rewrite your entire matrix, the linear matrix A, as a linear combination of these Hermite matrices, H0, H1, H2, so on and so forth, where each Hermite matrix is applying the kth order Hermite polynomial to each entry of the sample covariance matrix. Okay? Because original sigma is applied entry-wise to the matrix element, I can do the same thing. I'm just going to apply the Hermite polynomial entry-wise to each matrix elements. Now, what is going on with this equivalence principle is really saying the following characterization. Suppose D is a dimension of your input vector, and N is a number of these vectors. And here we consider a general setting where N can scale as D to the power of an integer. For example, L equal to 2, N will be scaling like D squared. This is a setting that we considered in our in-context learning setup. And then the equivalence principle is really saying the following thing. You can first write the nonlinear matrix as a infinite linear combination of these Hermite matrices. And here L is the exponent that we have that depends on the number of samples. Then, first of all, the first L Hermite components are low-rank components that we can safely ignore. Starting from the L plus H of L, the Lth order Hermite matrix, it is equivalent to a Wishart matrix. But then, interestingly, all the higher order Hermite matrices, they're asymptotically equivalent to an independent symmetric Gaussian matrix, so-called Gaussian orthogonal ensemble matrices, and they're also asymptotically independent. So we can combine all these higher order polynomial components into a single noise matrix. And this explains why we can represent A as a linear combination of a constant part plus a linear part, which is a Wishart part, plus all the higher order components are treated as a single noise matrix. Okay. And then this kind of a viewpoint has been applied in our work on understanding kernel ridge regression with polynomial scaling. And you can also explain the staircase phenomena and multiple descent phenomena depending on the sample complexity. The number of data can scale with dimension D, or scale with quadratically with D, or cubically with D. Then you have different scaling regimes. And the underlying mechanism for this equivalence principle is the following. So if you look at any Hermite matrix, you are just applying a polynomial to a matrix entry, and each matrix entry can be written as a linear inner product of two vectors. But because h of k is a polynomial, you can open up this inner product and rewrite it as a inner product of featurized version of these original vectors. So as a corresponding, you can still write the case order Hermite polynomial in the form of a sample covariance matrix. But the difference here is that each vector in this sample covariance matrix is not the original vector. It's a tensorized version of this original vector. But underlying mathematical derivation is very similar. And that is the reason why we still have the Wishart ensemble. Okay, and this is also the connection to our previous work, where each version of the featurized vector is a tensorized version of some lower dimensional vectors. Okay, I'll be happy to talk to you offline about the technical details, but this is just a summary of my talk. The first part, I presented our work of a theory of in-context learning by linear attention, and the main motivation is to try to understand the underlying mechanism of in-context learning that is observed in many large neural networks. And the second part, I briefly talk about the underlying mathematical mechanism or mathematical tools that allow us to do this kind of analysis. It has to do with so-called equivalence principle for nonlinear random matrix, or tensorized version of random vectors. So I'll be very happy to talk to you offline about the technical details. All right.
Right.
Thanks for your attention.
Any questions? And also people in Zoom? Yes.
I guess I came in late. What was the application for this? Calculation?
I heard it. So, can you repeat the question?
Yeah, what was the application for these calculations? Was it AI or something?
Oh, yeah. Okay, so this is the second part. Yeah. So we can call one of these A, right? And without sigma, X transpose will be sample covariance matrix, and there are a lot of applications where you want to study the sample covariance matrix. But why do we want to study the version where you apply entry-wise in the linear transformation to the sample covariance matrix? One case is chrono, if you want to study chrono method, and then in particular inner product chrono, and sigma will be the chrono function, for example, Laplace chrono. And then sigma of X times X transpose will be a chrono matrix. You want to study the spectrum of this chrono matrix, or the spectrum of chrono matrix in the context of chrono-ridge regression. And you can also consider a setting where you do a matrix factorization, so F times X and F. So F times X, you observe the product, but you want to do a factorization, maybe in factor analysis, but your observation model is such that you do not directly observe F times X, you observe some nonlinear version or noisy nonlinear version of this factor model. But you still want to do factor analysis. That could be another application, yeah. But my part of my motivation is this is just a new random matrix example that has not been studied, and we want to understand the underlying mathematical structure of these nonlinear random matrices.
Okay. Right. Other questions? Yes.
I have a question. Thank you, Professor Liu, for this talk. And I just have a question regarding to the in-context learning.
Yeah.
I remember you also have a slide showing that it's not always the case that the longer context, the generalization error be lower. And,
yes. Yes.
Do you in your theoretical result, do you have an explanation of this phenomenon?
We do not have an explanation, so we can even find out what is the optimal alpha because we have the theoretical curve. So in principle, we can just go to our theoretical prediction and then we say we set alpha, take derivative with respect to alpha, and we know what is optimal alpha. But we were not so sure whether this phenomena of monotonicity is an artifact of the linear attention model, or this is also a general phenomena that would even appear in nonlinear architectures. So we didn't look too much further into this.
Thank you.
Right. Other questions? One question is about simplification via linearization. So how difficult do you think is dealing with the nonlinear attention model?
Yeah, that's a good question. Yes. So we have some ideas, but most likely we will not be able to do this kind of a offline type of analysis. Here we just assume that we have all the data and then we going to study the actual global optimal solution. And I think a very tractable formulation to consider an online setting where you just have input sequences that come sequentially, and then you update your weight sequentially, and then you can study the dynamics of the evolution of the weight parameters. And in many cases, you can show that these evolutions can be summarized by a few lower order parameters, and there's a corresponding ODE limit. So it's very likely this is a case where things become very much tractable.
Okay. I also have a curious question about the nonlinear random matrix result you talked about.
Yeah.
So your intuition comes from the Hamid binomial decomposition, right? So I mean, I'm thinking about like just simple kind of sigma functions. Why not just do a local Taylor expansion and then
Good question. Yes.
lower?
Yes. This is a very good question. So indeed, indeed you can do it. That depends on the scaling with which you set these random vectors. So typically, xi and xj are two independent random vectors, and then their inner product is in the so-called CLT region, central limit theorem region. So you're going to get a Gaussian as a marginal law. But then, depending on scaling, you can scale the problem such that xi transpose xj is of size 1 over square root of d, in which case it's a very good idea to do a Taylor expansion around 0. So you can do a Taylor of sigma around 0, and then you have multiple terms. But there are other scalings, in particular in the random feature model, where the inner product xi transpose xj is of order 1. So in this case, and it's a random variable of order 1, so you cannot do a simple Taylor expansion around a fixed number.
Oh, I see.
Yeah, that has to do with scaling. Indeed, the initial studies of these corner random matrices is done in the region that you mentioned, just do a Taylor expansion.
Okay, great.
But that's considered the easy case because then behavior is essentially the kernel is equal to a linear function.
I see. All right, so any last question before we close? People on Zoom? All right, if not, thank you very much. Yeah, and have a nice day.
Thank you.
Thanks to you guys, and this is the last session of this master's seminar. We're going to continue next week. Thank you. Thank you, Yue.
Thank you.